Lines, circles, and parabolas find places to meet. We're going to use the method of substitution to solve systems of nonlinear equations in two variables. Let's look at this example. X squared plus y squared equals 25. There is a nonlinear equation. 2x plus y equals 10 is a linear equation. We want to find the points of intersection for those two equations algebraically. You should recognize that x squared plus y squared equal to 25 is the equation of a circle, which is centered at the origin and has a radius of 5. 2x plus y equals 10 is a linear equation. It's a straight line. We want to know, where does that line intersect the circle? First of all, from the second equation, I can write y is 10 minus 2x. And then I can use substitution. I can substitute that expression for the y into the equation of the circle. So I'll have x squared plus y squared, but for y, I'm going to substitute 10 minus 2x. So I have x squared plus the expression 10 minus 2x squared equals 25. Now I FOIL 10 minus 2x times 10 minus 2x, and I get 100 minus 40x plus 4x squared. So I have this first x squared plus 100 minus 40x plus 4x squared equals 25. The x squared plus 4x squared is 5x squared minus 40x, and then 100 minus 25 would be a plus 75 on the left-hand side equals 0. If I divide this equation through by 5, I get x squared minus 8x plus 15 equals 0. That quadratic equation can be solved by factoring. We have x minus 3 times x minus 5 equals 0, which tells me x is 3 or x is 5. Now if x is 3, y is 10 minus 2 times 3. 10 minus 2 times 3 is 4. So I have the point 3, 4 as one point of intersection. If x is 5, y is 10 minus 2 times 5. 10 minus 2 times 5 is 0. So I have the point 5, 0 as another point of intersection. So algebraically, I have determined that this line intersects the circle at the points 3, 4, and 5, 0. Here's the graph. You can see that the circle is centered at the origin with a radius of 5. Here is my line by the equation 2x plus y equals 10. And this line is intersecting the circle, as we said, at the point 3, 4 and at the point 5, 0. Here's another example. We want to solve this system of equations. Y equals x squared plus 1 and y equals 4x plus 1. You should recognize that y equals x squared plus 1 is a parabola that opens up and has a vertex at 0, 1. Y equal to 4x plus 1 is a line. We want to know, where does this line intersect the parabola? I can substitute x squared plus 1 is y, but y is 4x plus 1. So by substitution, x squared plus 1 equals 4x plus 1. Subtract 1 from each side and you would get x squared is 4x, or x squared minus 4x is 0. Factor out an x and you get x times x minus 4 is 0. So either x is 0 or x equals 4. If x is 0, the y is going to be 4 times 0 plus 1, which would just be 1. So 0, 1 is one point of intersection. If x is 4, y is 4 times 4 plus 1, and that would be 17. So 4, 17 is my other point of intersection. Here is the graph. This is the parabola described by the equation y equals x squared plus 1 And here is my straight line, my linear equation, y equals 4x plus 1. And you can see that they do intersect at the point 0, 1 and at the point 4, 17. Here's a system of equations where both equations are nonlinear, and we want to solve this system by the addition method. The first equation and the second one are both going to describe parabolas. If I add these two equations together, I'm going to get 2x squared minus 4x equals 0. The plus y and minus y cancel out when I add the equations. If I divide this equation through by 2, I'll have x squared minus 2x is 0, which factors x times x minus 2 is 0. So either x is 0 or x is 2. Now, the y is equal to negative x squared from this first equation. So if x is 0, y is negative 0 squared, which is just 0. So one point of intersection is 0, 0. If x is 2, y is minus x squared, so it is minus 2 squared or minus 4. So the point 2 minus 4 would be my other point of intersection. Here are the two parabolas. This one, y equals minus x squared, is the parabola that opens down. And the second parabola is this blue parabola opening up. You can see that they do indeed intersect at the point 0, 0 and at the point 2, negative 4. Here's an application problem. Instead of the lines, circles, and parabolas that we've been talking about, this problem actually involves a type of curve called a hyperbola. A system for tracking ships indicates that a ship lies on a path described by 2y squared minus x squared equals 1. The process is repeated, and the ship is found to lie on a path described by 2x squared minus y squared equals 1. If it's on both of these paths, then it is at the point or a point of intersection for these two equations. We're told additionally that the ship is located in the first quadrant of the coordinate system. So we know that the x and y coordinates of the point of intersection that we're looking for are both positive. How can we solve this system of two equations? They're both nonlinear equations. Both of the given equations describe curves known as hyperbolas, as we've said. From the first equation, I can rearrange the terms and write that x squared is going to be 2y squared minus 1. And then I can substitute that expression for x squared in the second equation. 2 times x squared will become 2 times 2y squared minus 1 minus y squared equals 1. Multiplying out, I have 4y squared minus 2 minus y squared is 1. The 4y squared minus y squared is 3y squared, so 3y squared minus 2 is 1. Adding 2 to both sides, I have 3y squared is 3, which gives me y squared is 1. I know I want the positive solution to that equation because the ship is in the first quadrant, so y would be positive 1. And if y is 1, I can then substitute x squared is 2 times 1 squared minus 1. And 2 times 1 squared minus 1 is just 1. If x squared is 1, and I know that x must also be non-negative, then x is going to be positive 1 as well. So the ship is at the point 1, 1. Here would be the graph. These blue curves and the green curve are the two hyperbolas described by these two equations. You can see that they actually have 4 points of intersection, but since I'm told the ship is in the first quadrant, this is the point of intersection I'm interested in, and its coordinates, as we have seen, are 1, 1. Solving these systems of equations where one or both equations is nonlinear is interesting, and I think it's especially interesting to solve them algebraically first and then to look at the graph to confirm our answer.